Thank you. As Matt said, my name is Michael. I'm on the Go team at Google working on mostly application performance, trying to make your Go applications faster. And today I'm going to talk about maps. You're all Go programmers. I'm sure you use a map in Go every single day. Pretty much every language has a map type either built into the language or in its standard library. And it's really a staple data structure. And in fact, what we've found from looking at a wide range of Go applications is when you look at a wide range of Go applications, on average, Go applications tend to spend about 10 to 15% of all their CPU time just doing map accesses and lookups and other operations. So there's definitely, we want these to be as fast as possible, and there's a pretty big potential impact here if we can speed things up. So in Go 124, which was released in February, we actually have a brand new map implementation in the Go runtime, a complete rewrite aimed at speeding up all the different map operations. So I'm going to walk through how a typical map works and how the new design improves on things, plus some unique challenges to changing a map in Go specifically. So just to be clear, when we say map, a map type, it's a bit of a generic term for generally any sort of key value collection. And there's different data structures that can be used to implement a map. When we're talking about Go's built-in map, that's a hash table. And a hash table specifically is a data structure that uses a hashing function to map arbitrary key values from a large key space into a smaller set of storage locations where we can store them. So a little bit of quick history on hash tables. Hash tables are not a new data structure. The hash table, and in fact hash functions in general, were first described in an internal IBM memo in 1953 by Hans-Peter Loon. In that memo, he was describing sort of the abstract concept of grouping items into small buckets in order to speed up searching for them. And a few years later, in 1957, Wesley Peterson, who was also at IBM, published the first paper about hash tables specifically. And interestingly, both of these two authors described actually slightly different approaches to how they would lay out and use a hash table. But both of those two approaches sort of cover the two major design directions that most hash tables today even still use. OK, so hash tables were first designed about 70 years ago, clearly a very core data structure that's had decades and decades of research. So surely it can seem like a hash table must be done by now, right? Several decades ago, surely we learned everything there is to know about a hash table, and everyone just uses the fastest possible hash table. But that's actually not true. That's actually what I think one of the cool things about computer science research is we keep learning new things about even core data structures and algorithms that we use every day. And so often we keep finding improvements that are either theoretical asymptotic improvements to algorithms or maybe ways of taking advantage of new hardware to speed things up. So that, if we jump way forward to 2017, is when several engineers from Google described what they called Swiss tables, which was their new hash table design specifically for C++. And it's really built on top of a lot of the core ideas from the papers from the 50s, but really focuses on trying to improve access and insert performance. And the Swiss table C++ implementation was open sourced in 2018. It's part of Google's Absale library, if you've ever seen that before. And it's gotten a lot of traction from different language communities sort of using this design to speed up their hash tables. All right, so let's walk through how a typical hash table might be implemented under the hood. So we'll look at just an integer map. And remember that we want to store sort of arbitrary integer values into a small amount of space. So that small amount of space, we're just going to start with a 16-slot array, which is our backing storage for this hash table. And on the screen here, the slot line is just the index into all of these locations in the array, and then the key line is going to be the keys we actually store there. And of course, the hash table has a value as well. I'm omitting that on these slides because in the data structure, the value is really not that interesting. It tends to just sort of hang off the side and get stored along with the key. OK, so we obviously can't fit every possible integer into 16 elements. So we need some mechanism to map an arbitrary integer to only one of these slots. And that's where the hashing function comes in. A hashing function is just a pseudo-random function that takes in any key and returns some 64-bit number that's we're going to use as a representation for that key. And then we can use this 64-bit number and fit it down to the range of the size of our hash table with just a modulo. That's where the modulo 16 is. We want to fit into one of these 16 slots. So let's insert some example entries. Let's say we're going to insert the key 23 into our map. We take the hash of 23 and mod 16 to fit it into the range, and we'll say that goes to slot 11. And now, just for these examples, remember the hashing function is random. So there's no significance to 11 here. I've just made up an interesting number that I liked. Any other number could have worked here. So don't think there's some special significance. Each of these hash values you'll see is just made up. So let's insert a couple more. This time we'll insert 47, which our hashing function says goes to slot 3. So we put that in slot 3. One more, we will insert 5. Our hashing function says that goes to slot 3. Unfortunately, we already put something in slot 3, so we can't use that. And this is called a hash collision. And a hash collision is really a fundamental part of a hash table, right? We're mapping a huge set of possible integer values into only 16 slots. So it's unavoidable that at some point our hashing function is going to tell us to go to a slot that we already used. And so every hash table needs some sort of approach to how it's going to resolve hash collisions. And this actually goes back to that history from the 1950s with the two different approaches. They took two different approaches to handling collisions. So the first approach, which was from the 1953 memo, is typically called separate chaining. And with a chaining approach, what that means is any entry that our hash function says goes to slot 3 is going to be stored in slot 3, but there's going to be some sort of a mechanism to add extra data to that slot. So typically, that would just be a linked list. So slot 3 is going to be a linked list of all the values that go at slot 3. Alternatively, the second approach from the 1957 paper is called open addressing. And in an open addressed hash table, all the keys are stored directly somewhere within our array. There's no extra data. And if a slot is already full, we need some mechanism to pick a different slot to use instead. And the function that we use to decide which slots to consider is called the probe sequence. And the most straightforward probe sequence is just called linear probing. And all linear probing means is just look at the next slot. So we're supposed to put this in, we're targeting slot 3. Slot 3 is already full, so we'll move on to slot 4. Slot 4 was empty, and therefore we can put our key in slot 4. And just continuing this example a little bit, if we insert yet another key that also is supposed to go to slot 3, we can't put it in slot 3 because that's full. We move on to slot 4, that is also full, and we move on to slot 5. And then we can finally insert it. And this can continue as long as necessary. And interestingly, Go's old map tables, old map implementation prior to Go 124 was actually a bit of a hybrid between the separate chaining approach and the open addressed approach. But the new Swiss table design is very much a form of open addressing, so that's what I'm going to focus on for the rest of this. OK, so we've been looking at map assignment so far, but note that lookups work pretty much exactly the same way. If we were going to look up 35 instead, we take the hash of 35, which tells us to look at slot 3. And now note, of course, there's a possibility of collision, so we need to actually double check if slot 3 contains the value that we wanted, which it doesn't. And since it doesn't, we follow the probe sequence from our probing function and look at slot 4 and then slot 5 until we find that's where we find the key we're looking for. And so far, we have this 16 elements backing array. But imagine that our array is now completely full, and we want to insert a 17th element. Now, obviously, we can't fit a 17th element. There's no space in our array. So we're going to need to grow this array. And typically, in a hash table, growing simply means doubling the size. So we would allocate a 32-entry array, copy all of our entries into the 32-entry array, and now we'll have space to insert our 17th entry. But if we step back a moment from the completely full hash table and say it's almost full, and here we can talk about the concept of what's called a load factor. And the load factor is simply a measure of how full the hash table is. So in this case, 14 out of the 16 slots are full, so that's an 87.5% load factor. And the main purpose of this metric is to give a sense on the impact that probing is going to have on our operations. For instance, imagine that we're going to insert another element, and our hash function says it goes to slot 0. Well, slot 0 is full, so we're going to have to start doing our linear probing. And we're going to have to probe all the way up to slot 10 before we find an empty place in our map. And that's actually more than half the entire size of this whole data structure, which is a pretty far cry from the 01 lookup time that we typically think of a hash table as having. And this sort of a long probe sequence when the map gets very full is kind of a core downside we have to think about and address with this form of a hash table. Now, we can mitigate this, these long probe sequences by growing our map early. We don't necessarily have to wait for the map to be completely full before we make it bigger. We could choose to grow the map when it's, say, 90% full or maybe even 70% full. And the earlier that we do our growth, the shorter the average probe length we can expect to be, because there's going to be more empty slots, and we can expect to run into an empty slot sooner. So any sort of hash table implementation has to sort of make this trade-off between how fast you want the operations to be versus space. Because if we grow the map early, our operations can be faster, but it also means that even in the best case, say we grow at 70%, and in the most full case, 30% of the storage locations are just unused and effectively wasted memory to some extent. So we have to sort of pick this trade-off between speed and memory. And that brings us back to the Swiss table design. Swiss tables are a form of open addressed hash table like we just saw, but they're specifically designed to try to minimize the cost of these probing operations. So let's look at how a Swiss table is laid out in contrast to the traditional hash table. So first, we have our backing array for storage. This is the exact same 16-element backing array we had before. The only difference is I've logically broken it up into groups of 8 elements each. And here, I have inserted the same keys that we had before. They happen to be in different locations just due to the way that inserts are going to work. And in addition to this backing array for our storage, we're also going to give each group a 64-bit word of extra metadata, which we'll call the control word. And each byte in the control word corresponds to one of the slots in the backing array. So for instance, slot 0 in group 0 is the key 45. And we store the lower 7 bits of the hash of 45 in the control word. So that's 23. And remember, I just made up the hash values. There's no significance to 23 here. It's just part of the hash of the value of 45. So we already have a bunch of entries in this map, so let's just look at how a lookup works. And let's say we want to look up the key 5. So in a Swiss table for our operations, we're going to need to take the hash of 5, and then we're going to break it up into break up that hash value into a couple of different parts that we're going to use for different purposes. We'll call them H1 and H2. And H1 is just the upper 57 bits of the hash value we got, and H2 is the lower 7 bits of the hash value. So just to give an example, if we say the hash of 5 was 345, the upper 57 bits are 2, the lower 7 bits are 89. You probably can't do that bitwise math in your head, but I promise it's correct. So we're going to use the H1 value to choose which group we want to look at first for our lookup. And this works pretty much the exact same way it did in the traditional hash table, where we just need to fit our H1 value into the number of groups we have. We can just do a modulo. In this case, H1 is 2, so 2 mod 2 is 0, so we're going to look at group 0. Now, once we've selected the group, we have to determine which of the slots within the group might contain our key. And unlike the old version of a hash table, there's no preferred slot in which no preferred slot within the group in which the key in which a given hash belongs. In fact, inserts just fill up the empty slots in order, which is why we have this sort of left-aligned looking behavior here. And instead of a preferred slot, we have this extra control word that gives us a little extra information. And we know that the h2 value we're looking for is 89. And for one of these slots to contain the key we want, its h2 value in the control word must be the same as what we're looking for. So we can just loop over the slots in the control word in order to look for a potential match. But we can do better than just a simple loop. And this is actually where the magic happens for a Swiss table. Now remember that the control word is just a uint64. I made it wide on the screen, but it's just a uint64. There's 1 byte for each slot. And what we really want to know is which bytes within this 64-bit value are equal to 89, which is our h2. And as I said, we could just loop over all of the bytes and do a comparison. But if you're familiar with SIMD operations, you probably know that this kind of a byte-wise operation within a larger value is precisely the purpose of SIMD. And you can actually do this kind of a byte-wise comparison with a single SIMD instruction. Now, SIMD is also typically concerned with larger values, 128-bit values, 256-bit values, and so on. We only have a 64-bit value. So it turns out that even on architectures that don't have SIMD instructions, there's not usually a byte-wise comparison instruction like this, but with a clever set of just standard arithmetic and bitwise instructions, you can still do this sort of parallel comparison in a fixed number of instructions. So we do this parallel comparison, and we can see that slot 1 has a potential match because the control word value matches the h2 that we're looking for. Now note that there is a chance of false positives here, right? This h2 value is only 7 bits. That means there's 128 possible values. So there's actually just a little bit less than a 1% chance that we will have a false positive match, and that we'll see the correct h2 value here, but the actual key won't match. So we're still going to need to go back and double check the actual key in the backing array and make sure that it matches. But that's totally fine. We had to do that even in the old version of the hash table, because even if you have a full 64-bit hash, there's always a possibility of collision. We need to make sure that we don't have a collision. So these parallel comparisons are really the core magic in the Swiss table. Remember that in the original hash table, excessive probing when the hash table gets very full was sort of the major pain point, or major slowdown point. And with this approach, we're basically performing 8 steps of the probe sequence all at the same time in a single instruction, which is a pretty impressive cost reduction. And in fact, the Swiss table design tends to have such a good improvement over a traditional probe sequence that it actually enables increasing the maximum load factor without hurting performance. So as I was saying, you can sort of choose, do you want to grow the map at 70%? Do you want to grow that map at 90%? You have this sort of trade-off. As it turns out, in Go 123, the point at which we grew was at 81% full. And with the new Swiss table design, we're able to increase that to 87%, which means we'll have better memory efficiency in the map type. But still, even having increased it to 87%, we still can see faster inserts and accesses just due to the improvement with this probe sequence. All right, so that is really the core improvement in the Swiss table design. There's lots of other clever tricks in there, but that's the big important thing to know. So now I'm going to talk about some challenges in bringing this to Go. So the original Swiss table design from 2017 was for C++, and it was targeting general compatibility with the C++ standard unordered map type. And Go's map semantics are a bit different from the C++ map and a bit more constrained in certain ways, which means we can't necessarily just copy and paste the code and rewrite it in Go. We actually have to fix some design challenges here. So I'm going to look at 2 different complications we have bringing this to Go. So first is about how we handle growing a map. So let's take an example here. Suppose you have an HTTP server, and each request does something with people's names, and we decide that we want to keep a cache of all the names that we've seen thus far. We're going to stick them all in a map. So we take our name, we put it in a map, no problem. This is usually going to be very fast. But at some point, there's a lot of names out there, right? This map's going to get big. So at some point, it's going to hit its maximum load factor and have to grow its backing storage. And in many hash table designs, including the C++ Swiss table design, growing happens all at once. And what that means is, at some point, there'll be one specific insert that will see that it's reached the maximum size and needs to grow the map. And during that insert, it will allocate a new array, and it will copy all the elements to the new array. Now, this is a very simple approach, very easy to do, but it has a big downside for large maps, which is we're copying every element in that single insert. So imagine that this map has 1 million names in it, and one of the inserts needs to grow the map. It's going to take a while to copy 1 million strings to the new map. And if it has 10 million names in it, it's going to take even longer. So what this means is, for our HTTP requests, is that there's this sort of unbounded tail latency impact. Most of our requests are going to be really fast, but then at this long tail, the couple that have to do growing can actually get quite slow. And in Go, we really want to have low and particularly predictable latency. We don't want to have these long tails. For instance, we have a low latency garbage collector, and so on. So we want to kind of try to avoid this problem if we can. Go, for many years now, has used what we call incremental growth in its maps. And that means that any one insert will have an upper bound on how much copying it will do in order to grow the map. So if we're going to double the size of the map, we might actually spread the copying over multiple insert calls so that each individual insert has a bounded latency impact. But it turns out the Swiss table design is not particularly amenable to growing incrementally, because the way the probe sequence works is dependent on the size of the map, on the size of the backing array, which means when we make it bigger, the probe sequence shuffles things all around. And so it's a little bit unclear how one might only grow part of the map and not the entire thing. So we solved this in Go with an additional layer of indirection. A Go map is not actually just a single Swiss table, but it consists of multiple independent Swiss tables that each cover a subset of the hash space. And each of those internal tables can grow independently of one another. So in an example here, if we have, say, 2 tables in our map, if an insert targets table 0 and that table is full and needs to grow, that table will grow all at once during the insert. But table 1 will be left alone, so we won't have done any copying there. And once a table reaches a certain maximum size, rather than growing that table, we'll actually split it into 2 tables and subdivide the hash space even more. And in this way, we have an upper bound on the maximum amount of growing work that any one insert has to do. All right, next is iteration. How do we iterate over a map? Now, this actually, it sounds pretty easy up front, because Go's maps have a randomized iteration order. And thanks to our hash function and the way the map is laid out, the layout of this backing array is pretty much random. So it seems that we can just go in order. We can just return slot 0, and then slot 1, and then slot 2, and so on. But what happens if we do something like this? Here we're iterating over our map, but occasionally we decide we want to insert additional entries, or occasionally we decide we want to delete an entry during our iteration. Now, many languages don't allow this at all. It's simply forbidden in a map type to do any mutations to the map during iteration. But Go does allow this. Here's a couple quotes from the language spec. I won't read these in detail, but the gist of it is if you insert during a map iteration, the spec says that newly inserted entries might be reported later during iteration, or they might be skipped over. And if you delete an entry during iteration, the spec says that that deleted entry will definitely not be reported later in iteration. So we have to figure out how we're going to support these semantics. Now, that naive approach of simply iterating over the slots in the array isn't going to work, because an insert might trigger the array to grow. And as I mentioned, growing shuffles the whole order of all of the keys in the array. And that means that we'll sort of lose track of which elements have we reported and which ones haven't we reported. So we can address this growing problem by having the iterator maintain a reference to the old table before it grows. So the iterator can literally keep a pointer to the table that it's iterating over. And that will keep the order. And when we grow the table, a new one is allocated. It has a different pointer. And so we can just keep iterating over the old one. And that keeps our order the same. And any new entries that are added are going to get added to the new version of the table. And so they're going to be completely missed. But that was fine. The spec said that was OK. However, if entries are later deleted after we grow, that's a problem, because they're going to get deleted from the new version of the table, but our old version still has them. So we might report stale values that have actually been deleted from the map. And the same deletion problem actually applies if you update the value in a map as well. The update will go to the new table, and the old one will still have the old stale value. So we can't just look at the old table, but we can take a bit of a hybrid approach. We can use the old table to decide which keys we're going to visit, basically our visit order. But once we decide on a key, we need to look it up again in the new table in order to decide if it still exists and in order to get the updated value if it has changed. So with these together, that pretty much covers all the core language semantics and gives us an iteration that actually is valid in the Go language spec. Now, there's a bunch more interesting edge cases here that I don't have time for. Things like we're going to pick a key out of the old table, and that key is a nan, a floating point nan. You go to look it up in the new table. Well, you can't look up a nan in a map because it doesn't compare equal to itself. So we have to do something about that. And I'll leave that as an exercise to the reader to figure out how to handle nans. All right, so that is everything. That's our whirlwind tour of how a Swiss table map works. Go 124 has this brand new implementation. Hopefully you have not noticed anything other than your program's going faster. Micro benchmarks are quite nice on this new map. There's about a 30% improvement to inserts and accesses for large maps. And in our suite of sort of full-size application benchmarks, which just may or may not use maps internally, we see a geo mean of about 1.5% improvement to complete application throughput. Now, obviously, it took quite a while to get to the right design for a new map. I certainly had a lot of fun working on writing a new map, but it was not just me. We had a bunch of people I want to thank. Yunhao, PJ, and Andy all built prototypes to sort of explore the design space of how can we make this kind of map work with Go. And then Peter Mattis at CockroachDB took some of those ideas and some of his own and actually built a public Go package that folks were using for quite some time that provided a language spec compliant Swiss table map prior to 124. And then that design kind of formed the basis for what ended up in the Go standard library in 124. All right, thank you all very much.